OK， 那我们就开始。所以，我们假设 H 是 Wigner matrix， 就是它是等于HIJ， 然后 expectation。我假设这个我现在都是谈 real 的 case，complex 也是一样，然后 quaternion 其实也是一样，但是主要是做 real。那我们假设这个 HIJ exponential of constant HIJ expectation 是小于无限大，那 times square root n。Okay, we assume that exponential square root n Hij is less than infinity. So, in other words, this Hij, Hij has, roughly speaking, you want to think about the H is 1 over square root n of Xij, and this Xij expectation equals 0, and the mean variance equal to 1, and the probability distribution of Xij has exponential tail. And this condition is not important. This actually is not important, but I just assume this for simplicity. So I'll comment later on. Okay. Now the main theorem is the following. So I also should recall the definition of the k-point correlation functions. Xk. Let me check what's my notation. Yes. Okay. So the k-point correlation function is defined to be integration of n-point correlation function n of lambda 1 x1 xk and yk plus 1 yn. And where probability Pn of lambda 1 to lambda n is the probability density of the eigenvalues is probably induced by a law of Hn. Hn is this one. So you have a matrix, and so from this matrix you can solve the eigenvalues equations. You get eigenvalues. So eigenvalue has a density. This is called Pn lambda 1 to lambda n. So I'll remind you that there's no explicit formula for P1, for this Pn, except the Gaussian case. And in this case, the Gaussian case, in this case, is the GOE. It's Gaussian orthogonal ensemble. Now, so this, and last time, in this special case, the Gaussian case, we know this one is given by orthogonal polynomials. But I'm not going to repeat this. And so now, so the main difficulty here is this one has no explicit formula. And then I should add a remark that I also consider this Pn. Now Pn lambda 1 to lambda n. You can view this as in two ways. One is if you think about lambda 1 less than lambda 2 less than lambda n, and because you can order the eigenvalues, or you can also symmetrize it. Symmetrizing means in the beginning you just define this over this, over this simplex, but then you can define everywhere by symmetrizing. So in this definition, this is symmetric version. Because otherwise you have to, this 1 to k is not the first k eigenvalue, it's actually arbitrary. So this is called a k-point correlation function. In probability theory, it's called a k-point marginal. So the main theorem is if you can compute take n here. Oh, sorry, you should keep n here. And you take k-point correlation functions, and now you fix energy E and plus alpha 1 divided by n rho semicircle alpha k n times rho semicircle of E. And you take the same thing with respect to pkn, but you put a Gaussian case and do the same thing here. And this object will converge. You take a test functions of alpha 1 to alpha k. You integrate over the alpha k. And then I need a small average actually. I need let me see. Oh, I should put a v, sorry. Excuse me. V here. Oh, okay. Sorry, just a second. And now I integrate over v. And E minus B and E plus B, 1 over 2B. Okay, so I take limit. I will explain what's B and go to infinity. It's actually 0. And B is, what is B? B is bigger than, for any B, for any B less than n to the minus 1/2 plus epsilon. Oh yeah, this is V. That's right. So what's the idea? The idea is if you take a k-point correlation function and the scale 1 over n, here you divide by 1 over n. So be careful because, let me remind you. So the probability density is the probability density for Hn. In other words, so this one is equal to 1 over 2 pi square root 4 minus x squared times correlation functions So the semicircle law is the probability density of eigenvalues for. In other words, there is a semicircle, and then there will be more eigenvalue in the middle, and there will be less here, and actually, eventually, there's nothing outside. So this is probability density. So be careful, they are altogether n eigenvalues. So this is last time we proved this. This is the Wigner theorem. This is the Wigner theorem. Okay. So, and now if you want to understand the behavior of a local structure, so your correlation functions, you have to look at the correlation function at the scale 1 over n. So what we say is, if you look at correlation function at the scale 1 over n, then this one will converge weakly to a Gaussian case. And now, so converge weakly because you do a test function. So this is test function. This is smooth functions with complex support. So take smooth function with complex support. You take any matrix and you subtract the same thing in the Gaussian case. And then you say you take a test function, your average is going to 0. But on the other hand, the theorem is slightly weaker. It's in the sense that this statement, what I'm hoping for, is not quite correct. It's not quite. I mean, we didn't quite prove that. What we prove is that in addition, if you take an average over energy E in a small window of size B, and this window size B is less than n to the minus 1/2 plus epsilon, then the statement is correct. Okay. And so this, I forgot to say this E, and this also E, for any E belong to the interval minus 2 to 2. Okay, so you had to be, this theorem is correct in the interior. Now, let me try to make some remark. Remark one is, so there's a similar theorem. Near the edges. In other words, this theorem also correct for the largest eigenvalues or the smallest eigenvalues. And that's the so-called Tracy-Wheeler distribution, which give you the, so it's giving the Tracy-Wheeler distribution. Okay. The second remark, maybe I should write here. So the second remark is we only need expectation xij to the 4 plus epsilon. That's infinity. So this is sufficient. So you don't really need the exponential decay. Exponential decay is only for convenience. Actually, you can go down to this. But the conjecture is it's only the second moment matter. If you have this, it's enough. So this is open actually. I think this may be doable. Actually, this problem may be doable. It's a bit technical, so I don't really like it. But so, and remark 3 is this B can be improved to replace by without much. It's with similar idea. So this means you can almost take out this You can almost take out this average. Because once you go down to n to the minus 1, then actually you already look at a scale or local scale. But with similar idea, you can go down to n to the minus 1 plus epsilon. Of course, every time I write this, epsilon has to be positive. And number 4 is it's actually the average in B can be totally removed. So this is a major work. So this needs the major new idea. Okay. In the complex, in the real symmetric case. Okay. Now, for complex case, the Hermitian case, this follow from there's a formula. There's a formula called Itzigson. You know, don't trust me with the spelling. Itzigson Ruber. Itzigson Ruber. I forgot. There are lots of names. Itzigson Ruber. And there are another 2 or 3 men. 3 names. And then it's also called Harishchandra. Harish. Formula. This is something very strange. The random matrix, all the random matrix theory in beta equal to 2, this complex case, is always the simplest case. And then and that's because there's explicit formula. This explicit formula it holds only for complex. It holds only for the in the case of complex. It's actually only for the unitary group, but it does not hold for the orthogonal group. I don't know why, and actually I don't really understand this formula. It just somebody say there's a formula, and so I can't. But on the other hand, this formula, the people has never been able to do this in the real case. I think in the real case, I think it's probably there's a formula, but it's so complicated and it's very difficult to use. So what we are doing is what we're doing here, we didn't use these explicit formulas. So, and then remark number 5 is it's actually this xij squared. If you write this equal to Sij, then Sij can be very general. So this I would not say any of this. So I try to sketch a proof of the theorem in this form today, and none of this. I will not say any of this extension today. And I think this will. It's a bit long story. So. Okay. So now let's go back to the technical part, and which is consider this Stiegel transform. So any questions? And anyone? Well, if you take of course, the correct statement, what you want to do is without this average. You want to say this is correct for fixed V. But because mathematically you cannot do this for a fixed point, then you do a small average. And so there's no importance. The importance is you can't do the case without it. And actually, it took another, I think this theorem was proved in 2009 to 2010. And this one, in the case we took out this, can be totally removed. This is just a preprint. It's still not published yet. It's, so there's, you know, in mathematics, if you ask some very technical question, with very fine detail, then it's very hard to do. And now, if you ask me whether it's important to remove the average, it depends on what you mean. It's, I think physically, of course, you don't believe that you don't believe any weak convergence is really weak. It's not strong. But on the other hand, in mathematics, you can ask some very specific question. You cannot answer with a theorem with an average. So you have to, so technically you have to remove it, and so. And by the way, the statement of this theorem has to be take weak convergence, because in the discrete case of Bernoulli random matrices, this is just plus minus 1, for example. Then if you don't test this with a smooth function, then the theorem is not even correct. And so, okay. So now I will sketch the. So now let's go back to the Stiger transform. Oh, remark 3 is here I state this is between minus 1/2 plus epsilon. That's what?
1/2 is good or not?
1/2 is the smaller the b, the better. The smaller the average, the stronger the theorem.
The first condition is have more freedom.
But you take a more average. Your statement, you want to prove that this is correct for fixed v. You want to prove this without the average. This is the best statement. And
Second statement is also average.
yes, but you average over smaller windows.
To understand v could be arbitrary number, hopefully it cannot be smaller.
Well, this theorem is correct only if you take the b.
Or maybe
Only, only if you take a bn. B is a number depending on n. And this number has to be less than n to the minus 1/2 plus epsilon.
same size or smaller.
What?
I don't understand the one is better why it could be replaced by the worst one.
I mean, this of course this if I replace b by this is a stronger. This is a stronger result, which of course will not follow from the theorem. Will not follow from the theorem as I stated here. But what I'm saying is you actually can prove this theorem also under this condition, under this assumption, without changing very much the structure. So this theorem is almost correct. This theorem is correct actually if you change this n minus 1/2 to n minus 1. And the proof is only small changes.
I don't understand the logic.
I don't understand your logic either. Your theorem says I take a windows, I need to average I need to average n to the minus 1/2 plus epsilon, then it's correct. Another theorem says I average over a window of a size n to the minus 1 plus epsilon, then this is correct.
So maybe b is for the same size, not smaller.
I think that should be a lower bound b.
Oh, bigger than.
Thank you. Thank you.
Sorry. Oh. Okay. Thanks. So this is what I mean. Yes.
Comment more about the difference between real case and complex case.
You mean why there's a difference? Oh, sorry. So this is the following. Sorry. Now, the problem is the following. So the question is, if you take a metric A plus B, and B is any fixed matrix, it doesn't matter what it is. Okay. And A is Gaussian. A is GUE. Okay. And then you look at eigenvalue distribution lambda 1 to lambda n of A plus B. So there's explicit. So there's a formula. There's a formula. Give you an explicit expression of this A plus B. And this formula is not correct if I replace this GUE by GOE. And you will see that later on, it's very important to consider perturbation of a matrix by a Gaussian matrix. So study matrix of this type. So study matrix of this type is important for proving this theorem. This theorem will be proved. I mean, if you think about this, B is H. You take your original metric H, you add the perturbation. This is something you add. You add the perturbation. In the complex case, you add the GUE. In the real case, you add GOE. And then from this explicit formula, you find that H plus A has satisfied the theorem. And then finally, you should try to remove this perturbation and then say H satisfies that result. So in this procedure, it's very important to understand the matrix eigenvalue for this one. And in the complex case, there's explicit formula given by this Sixer-Ruber Harish-Chandra formula. And in the case, if this A is GOE, if this one is GOE, there is no such formula. And if somebody can find the explicit formula in the case of GOE, then everything we did, you can remove it. And actually, I should say that there's some sort of formula people has for a real case, but it's so complicated, it's not even know what to use. And also even this symmetric case, this formula actually is not that easy. But you know, it's not easy, but it's actually fairly usable. So, but I cannot explain this because I don't really understand this why this Lie group in the special case of unitary case has such a special formula. This I don't understand, and I don't think anybody really understands. Because if you really understand, then you understand why this is correct in the case of complex but not real. But I look at the literature, every paper just says nobody knows how to do for the GOE case. What? Sorry?
What's the main tool?
What's the main tool?
Okay.
Well, it's I don't know either. This Harish-Chandra formula, it's among the Lie group. All these eigenvalue has some special relations. I have no idea what they are, and so I don't really know. I mean, if you want to, I need to prepare this for a major lecture. It's more than, you know, this is something I can't really say what it is. I also don't know why it's correct. Okay. All right. Okay. So all right. So now we get to the Stiger transform. So so Stiger transform, you define the, if you have a probability measure mu is a probability measure. So we define the Steele transform mu at z is equal to z minus x minus z, sorry. X minus z mu. Okay. All right. So now you take the mu. So if you take the mu, it's a summation of delta x minus lambda j from 1 to n, and 1 over n. And then this s of mu, it's, you call this mn of z, it's just 1 over n summation of j from 1 to n of lambda j minus z mu, just this. Okay? And now, so this is equal to the trace of g of z, and g of z is 1 over z minus h, and 1 over n. Okay. So, and then, so this is well known that, so this is a fact. You define the MSC of z is equal to rho SC of x dx of x minus z. Then MSC of z plus 1 over MSC of z plus z 0. Okay. Yes. Wow. Okay. Okay. And then you can solve this explicitly. So wow. So let me just write it. Okay. So now our idea. So this is a fact. Now I write the z equal to e plus I eta. So the fact is, if you compute mn of z minus msc of z, limit as n goes to infinity, this will equal 0 for any eta fixed. This is more or less due to the Wigner theorem. And this goes to 0 with high probability. Actually, we didn't really say what is meant by high probability, so I will make this precise later on. So the Wigner theorem, you can restate it by saying that the Steele transform minus this one, semicircle one goes to 0, and with eta fixed. And now our goal is we want to study this same thing. For eta equal to n to the minus 1 plus epsilon. So this is the main task. And now the question is why. So reason is the following. The reason I think I mentioned last time, this function lambda j minus z, okay, let me try x, is equal to x minus e squared plus eta squared. If you look at imaginary part, it's equal to that. So this is this at the point E, it's a and then the size here is eta, and the height is eta minus 1. Okay? So this means the smaller the eta, the more precision, more information I have in understanding the original structure of this lambda j minus z. So that's the key idea is, and so So roughly speaking, if you look at this summation j from 1 to n, lambda j minus z divided by 1 over n. This, roughly speaking, is a number of eigenvalues in E minus eta and E plus eta divided by n. Because the imaginary part of this is roughly this. Do we agree? Yes or not? I mean, this is you have to agree that what we are trying to study. I mean, never mind the proof, but just this was. Maybe I should tell you that. Why are we trying? You know, this was the first question I asked when I go into this field. It's so now, if you look at green functions, the green function, roughly speaking, if you take lambda j minus z, it really just because each one, the imaginary part of this one is x minus e plus eta. So this means you take an e and you take a window eta, and out of this is eta minus 1, so this is the density. If eigenvalues lambda j is here, then this lambda j, then this imaginary part of lambda j minus z is basically counted as eta minus 1. If lambda j minus z is less than eta. So it's inside you count as eta minus 1, but outside you count very little. It's almost 0. So this one is really, you take an energy E and you fix a window size eta, and then you ask how many eigenvalues are inside. So that's really what it meant. Okay. And so so if you count the number of eigenvalues inside here divided by n, actually divided by n eta, sorry. Divided by n eta. No, I think it's actually divided by n eta because this one, sorry. Let me write it again. X minus z is equal to eta minus 1 if x minus z, x minus e is less than eta. Okay? So if there's eigenvalues in this window, e minus eta, e plus eta, you count it as eta minus 1. And then and then here you sum over that, you divide 1 over n, divided by 1 over n is n eta, and the summation give you the number of eigenvalues here. So this is the quantity you want to study. So the basic message is, if you want to understand the eigenvalue structures, you first have to, you look at green functions, or this, and then you start to look at this eta become very smaller and smaller, and this is a key point. So. So I think, you know, I'm trying to explain to you that when we started to do the random matrix, and so there was no estimate on this green function except this Wigner theorem. So now the question is, you are trying to study. Don't forget you are trying to study this problem. In the beginning, you're trying to study this problem, and so. At the time, most people just try to find the formula for this guy, and so that you can analyze. But on the other hand, we completely given up to study this problem. Instead, we look at green functions. We look at green function, and we start to ask the question: when the green function, when this eta becomes smaller, can we get an estimate on this guy? So this is the standard approach in doing. If you are analyst, you start to try to derive some sort of a priori estimate. You try to understand the question. You try to understand the question. This eta is bigger than n to the minus 1 plus epsilon, because you don't want to go to study the real detail of the distance between two eigenvalues. You take a scale slightly bigger, and you want to get some information. So this is the idea of once you are trying to approach your problem by doing analysis, always you always try to derive some a priori estimate in this way. And so this was the first question we are asking, is try to see if we can get an estimate like that. And the theorem is the following. So this is the theorem. So let me try to say this theorem is in, this is theorem 4.5 in my note. Theorem 4.5. Theorem 4.5 says if you compute the Gij of Z, of course you can also consider the, well, let me state the Mn of Z first. Mn of Z minus MSC of Z. This less than 1 over n eta times n to the epsilon. So probability of this bigger than this is less than n to the minus c for any c. And now, and the z. I should give a domain of z, and z is and z is let me see just a second. I should find the domain. And eta. For any positive. Now, if you look at the note, it's stated slightly differently, and also including the edge. But here I only talk about the estimate. I did include what's the improvement near the edge. So this statement like this. Let me see. Yeah, that's right. That's correct.
Second A I N.
Oh, n. That's right. Sorry. Thanks. So, and now as a corollary, we get the following theorem, which is yeah. The theorem is so this is theorem 4.5. It's called this is theorem 9.5. It says the following. So the probability. So define gamma j to be equal by the equation j over n equal to minus infinity to gamma j rho semicircle of x dx. Okay, so this is the so gamma j is the classical location of j's eigenvalues under the law semicircle of x. So in other words, you take the semicircle law, and if you integrate up to here, and if this one give you j over n, and this point, you will call this point gamma j. So this is what you expect the location of j's eigenvalue is. Okay? And the theorem says the probability of if there exists a J such that lambda J minus gamma J is bigger than J minus 1/3 n minus J minus 2/3 and n to the epsilon is less than n to the minus d for only d. Okay. So now, so this is called the rigidity of eigenvalue. So let me explain what's going on here. It's a
One third and second third and two third.
what?
In the
Oh, why you have a 1/3, 2/3? Okay. Yeah, this is what I'm trying to explain now. The reason is the following. The reason is, if you look at this, now the typical spacing of eigenvalue here is n to the minus 2/3 near the edge. This is because the square root behavior here. And in the center, once you cross center, the typical distance is n to the minus 1. So once j equal to 1, actually I shouldn't write, once j equal to 1, you only get the n to the minus 2/3. So if you think about this, this is j for j less than n over 2. Because once j bigger than n over 2, then you count it from this side. So I only wrote half of it. So what he says is the typical eigenvalue space is n to the minus 2/3. And the typical eigenvalue space is n to the minus 1 here. And then if you start to look at your location of gamma j, this is the prediction from the semicircle law. And then this is the real location of lambda j. Then their distance, if you are in the bulk, the distance is basically n to the minus 1. Of the order n to the minus 1, you can make some error n to the epsilon, but that's it. So that's why it's called rigidity. It means that every single eigenvalues are pretty much located what it should be. I mean, if you compare with the Poisson distribution, this is completely different. Poisson distribution, you will not prove any theorem like this. That's because if you take n particle, go like a Poisson distribution, somewhere there's a big gap, and somewhere they are very, very close. So this is a completely different from the Poisson. So this gives you the rough location of where the eigenvalue is, and so that's the rigidity. And this rigidity coming from a green function estimate. You know, I always understand mathematics from the point of view of differential equation. So that's why I try to estimate the green functions. So to estimate green function is a natural direction. It's a natural method for me, but it's not necessarily natural for other people. So if you look at Terry Tao's approach, he didn't touch green function at all. He has no green function estimate completely, nothing, because he's looking at problem from this high dimensional geometry, and so from this more like this balance space consideration, high dimensional geometry. But I think in this problem, look at problem from differential equation point of view still give you much stronger result. And so okay, so now so I want to explain two things. One is I should erase this. what is the first thing is why is this equation correct? Why is this equation? Of course, you can explain solution, but why is this correct? And then the second thing is when you get the green function estimate, how can you go from green function estimate to a precise location of the eigenvalues? So this idea to go from here to here, this is a very cute idea. It's not due to us, but I mean the theorem is due to us, but the tool is not due to us, and it's also quite general, and it's very it may be useful in other contexts. So this is very nice, and this one is more this one is a bit harder. So so let me start with this, and then I will explain a little bit of this one, and then I hope I can start the Dyson-Brownian motion. So I think let me start with this guy. Okay. Now, I don't know if you, so for students learning the harmonic function analysis, so let me ask you a question. How do you, suppose you have a metric H, a symmetric. All you can think about is the operator. You know, function analysis more or less it's the same as linear algebra. It's just put some topology. It's basically the same. So how do we define f of h? When h is when f is say some nice functions. So how do we define it? By eigenvalue of h, yes, and but actually, so this means you have to diagonalize this h completely, right? But on the other hand, in most of the time, you cannot re-diagonalize it. So what do you do? So of course you can diagonalize and define it using eigenvalue, eigenfunction. This is what you learn in the spectral theorem. But there is a way is to, if you compare h minus z and f of z dz over the contour integration, right? Then you can define it because you, of course, you need 1 over 2 pi I. And so here are the spectrum is here, and then you take a contour, enclose this, compute this exactly give you the f of h. So this is very nice. The only trouble is actually this formula is very difficult to use. And the reason is because this is difficult to use is because it's difficult to use because it's a complex contour integral, so there are lots of cancellation and oscillation. So this formula is hard to use. But there's a beautiful formula called let me try to find it. This formula, it's actually a bit unfair. It's called the Hereford-Schrechen formula because I don't think they are the first. This formula is well-known classical formula. Okay. So the formula is the following. The formula is f of h is equal to dz bar. And the f tilde is f tilde is called I forgot its name. Just a second. F tilde of x And chi is the function. This is 1/2. It's 1 here. It's 1. Then it's 0. Okay. So this F tilde is called, I forgot its name. It's something called the pseudo holomorphic extension, or I forgot exactly. Pseudo analytic extension. Extension of f. And f is the original function f. So f is I think f is a C2 function. I forgot exactly. I think C2 is already enough. There's one derivative here, so probably 1 or 2 derivatives is already enough. So this formula, you have this. So with this formula, this implies that you can compute the summation f of lambda j from 1 to n, 1 over n, and this will equal to 1 over pi, and the dz bar f tilde x plus I y, and divide by lambda j minus z. Sorry, I write like this. This 1 over lambda j minus z, summation over j 1 over n, and dx dy. And this one is 1 over pi of d z bar f tilde x plus I y of m n of z dx dy. So that's why there's importance is in this, to get this formula. In other words, now you can take your function f. You can take your function f is a counting functions, like this is 1 and almost go down to 0. So you can take f like that. This is 1 and then you go down to 0. And there's energy E here. So you can count the number of eigenvalues here using this formula. So it tells you that from the stereo transform or from the green function, you can give a precise. There's a very precise formula for the eigenvalues. For the summation of eigenvalues, and from this formula, then this formula is the key. Once you get that, you plug in that formula, because what you say is this mn of z can be replaced by msc of z. So once you can replace this by this one, and then this one will just count how many eigenvalues for the Wigner random matrix, and if you use this one, you will count the eigenvalues given by the semicircle law, and so that's why you get a comparison. I hope it's the logic, okay? I mean, this formula, of course, one has to prove it, but actually, I strongly suggest that if you took compare analysis, actually, if you know the calculus, know the green theorem, you can actually prove this directly. You don't have to go to read any paper or whatever. You just prove this by compare analysis. That's it. It's because even though I write the h here, but you can think about h as just a number, because you want to prove the theorem. The only thing you need is because you can diagonalize, as you say, you can diagonalize. So this formula, you only have to prove this for a number. So this h, you can think about this h is a number. This h is a number. So with this is a number, it's just something like a Cauchy integral formula. But instead of Cauchy integral formula, you are integrating over a two-dimensional space. And then it's something quite similar to Cauchy integral formula. but it works for non-analytic function. First, this works for non-analytic function, and the second, this is two-dimensional integration, so the singularity is much weaker. The singularity here, h minus z, become much weaker over two dimensions. And previously, if you use this formula, you have to worry about, because this is line integral. But if you take a line integral, then when h close to z, this will be very singular. So this formula is always much better. It's almost always. Oh, you worry about I lose the complex analysis, good probability complex analysis. Yes, this could happen, but I'm just telling you that in our experience, it's almost always better to use this one. There are some rare occasions we use this one which give you a good result, but in most cases, this formula is better when you are doing analysis. But of course, if you want to do lots of contour integral, you want to have explicit formula, the contour integral is always much better. But so Stiger transform.
Indeed, it is a Cauchy integral.
我听不到，年纪太大了，有没有人要 repeat 一下他的问题？啊，好，等一下我们再说好，因为我听不太清楚你讲什么。我只听到电风扇。Okay, so I think now is probably a good time to start. So let me just conclude what I'm saying. This always is from the green function estimate you can get the rigidity eigenvalues, and the rigidity eigenvalue of course is still far from what you want to do here, but it give you a sort of the a priori estimate what you need to do that theorem. So in next hour, I will start to explain what's this idea, and then I will introduce the Dyson-Brownian motion. And I don't know how much I can go, but I think I can define the Dyson-Brownian motion and mention one key property. But I don't know if I can prove this theorem, so this will be okay. Okay, so I think I will not. I don't think I have time to talk about this estimate. And also, the idea I can say about, I can say a few words about the history and so. So the idea is, so this estimate for eta bigger than n to the minus 1/2 plus epsilon. So this case can be done by, was more or less proved. By a combination of there's a work by Bai Zidong, and also combination with Gilnet and Zaituni. So this is estimate by, their method is by concentration. So they are using the concentration idea based on log-Solver inequality. And the Bai and so on, they, I think Bai has been spending his life to try to improve estimate on the Stiger transform, but somehow the idea and his approach was much more convoluted, so he couldn't see the how to get eta become smaller, and so. And now, so I will not talk about this because this is going to, explain the idea will take about 20, 30 minutes is already. So maybe I should tell you what's the Dyson-Brownian motion, which may have some more general appeal. Okay, so. So I start with Dyson-Brownian motion. Now, the Dyson-Brownian motion, the idea is very easy. So you take a matrix H equal to 1 over square root n of xij. So now, suppose this xij is xij of t, which is express Brownian motion bij of t. And now, no, as I written, it's a small bij. And bij, this is a standard Brownian motion. Okay. And so now the question is, what is the dynamics of eigenvalue lambda 1 of t to lambda n of t? So this was a question of Dyson, and the statement is the following. The statement is, if you look at the stochastic dynamics, then it's equal to square root 2 So the theorem is the following. So the eigenvalues satisfy this dynamics, and this is by Dyson. I think Dyson proved this in about 1960. So now, so the question is, how do you derive this formula? How do you derive this? So the question one is, what's the derivation? So the idea, so let me try to explain to you the idea, how to derive this formula. The idea is the following. So if you look at the eigenvalue equations of H of U alpha, U lambda alpha, U alpha, this actually is, if you took quantum mechanics class, and you know the second order perturbation formula and plus Ito formulas, plus Ito's formula, then you will get this formula. So the proof, roughly speaking, the proof is by perturbation and the Ito's formula. So I'll explain what the perturbation means. So if you look at the equation like this eigenvalue equation, and everybody has a t dependence. Okay. Now you take a derivative in t. So this implies h dot u alpha plus h u alpha dot equal to lambda dot plus lambda u alpha dot. Okay? So this is obvious, it's correct. And now you multiply this equation by u beta. So you get u beta h dot u alpha plus u beta dot h equal to lambda dot, because the u, actually this term is 0 because the beta now equal to alpha, and alpha and beta are orthogonal, and then you plus lambda plus u alpha dot u beta. So get this equation 1. And equation 2 is you multiply this. This is beta not equal to alpha. Okay. You can also take beta equal to alpha. When you take beta equal to alpha, this beta equal to alpha, this is u alpha, h dot u alpha. And plus this term, when alpha equal to beta, this is u alpha h beta, so this is lambda alpha, u alpha dot equal to. Now on the right hand side is lambda dot, because u alpha square equal to 1, and plus lambda u alpha dot. Okay. So these two equations. Am I correct? So I multiply u alpha, so that's right. U beta, this one, this equal to that, so that's correct. And then lambda alpha dot, yes. So this term is 0. And this term is 0. That's right? Yeah. Okay. So this term is 0 because you normalize your equation u alpha. This is equal to 1. So you take a derivative, this is equal to 0. So you can solve lambda dot. And then from here, you can also solve the u dot. Okay. So you get lambda dot formula, and you also get u dot alpha. There's also a formula, just from here. This formula says if you compute h u alpha dot, and they acting on u beta, you can compute. So in terms of h dot, so this means this component, because then you take an inverse. So what should I say? I think it may be, okay, let me try to explain this in slightly nicer way. So look at this formula. Okay. Now you know what's lambda dot, because lambda dot is given by this form. So from here, you can get u h minus equal to so this implies u alpha dot so you can compute this, okay? So you have a formula for the derivative of eigenvector and derivative of eigenvalues, and this formula is called this formula lambda. This is called the first order perturbation formula. And this one is called the second order. Okay. This is a standard. You know, the physicists spend their life using perturbation formula, but this is not very popular in mathematics. And the reason is, one key reason is because I mean, if you written this as a derivative, it's rigorous, but otherwise, the physicists always apply this to a perturbation. So whenever you change h by something very large, so the perturbation in mathematics is difficult to justify, but anyway, it's extremely useful. And for some reason, it's just not very well known in mathematics. But anyway, so here is completely rigorous because it's just derivative. And so now you want to compute d lambda alpha. So if you, according to Ito's formula, so you compute you can use d square lambda alpha and d H I K D H L J, and then plus D lambda alpha D H I K and D H I K. And this one, and then, so at the end, so I will not do this, so this is quadratic variation. So at the end, so I will not follow through this calculation because using this perturbation formula, because you can compute lambda dot and you have a dot. At the end, you will find out, I mean, this is some calculation, you'll find it's 1 over square root n summation I k u alpha I u alpha k d db I k minus plus 1 over n summation lambda alpha minus lambda beta, beta equal to alpha dt. So you get this formula. So all I'm saying is, I think this is probably hard for you to follow exactly this calculation, but all I'm saying is this actually is in page 65 and 66. 65 to 66. But these calculations, if you know the Ito's formula, and then you apply Ito's formula, you find that you compute the first derivative of lambda, and you also compute the second derivative of lambda. But the second derivative of lambda is connected to the derivative of eigenvector. So this one can be computed using this information, because you can see the lambda dot depending on u alpha. So you take second derivative would depend on u alpha dot. So the derivative here would depend on u alpha dot, and then you use the second order formula. You put it together, and then at the end you get this formula. So this is a slightly long calculation, but it's basically just one page calculation. And now the idea is this guy. This guy. So you let so you define. So you redefine this b alpha. This is db alpha equal to summation I k u alpha I and u alpha k db I k. Okay, and then you can check that db alpha, db beta, this quadratic variation is equal to delta alpha beta, and so this means so this implies that b alpha is a standard Brownian motion. Okay, so that's the idea. I mean, rigorous proof has some small difference, small details, but roughly speaking, this is the idea. So you get this. You see, what I'm trying to emphasize is the Brownian motion of the alpha's eigenvalue comes out is because this linear combination of summation of ik of db ik and with these eigenvectors. So you all this put together, you call this a new Brownian motions. Then you check the new Brownian motion has this quadratic variation of the standard Brownian motion. So this means that these are independent Brownian motions. So that's the idea. I mean, it's not you after you. I mean, you may. I don't know if you feel that whether there's some curiosity, because this d lambda I, this dbi. So this is the. And then you can ask where this Brownian motion come from, because in the beginning here your Brownian motion of ij, but it only has one of. These are n square of them. These are n of them, and the connection is this Brownian motion is actually given by this formula. Okay. So my suggestion is you probably don't want to worry too much these derivations. And you should take this for granted, that there's such a formula for the dynamics of the eigenvalues. Okay? Now, so let me add some small remark. So you can also consider dHij is equal to dBij minus 1/2 Hij over 2 of dt. Let me check it's over 2 or I think it's over 2. So this is so-called yes, this is the Ornstein-Uhlenbeck process. If you take this Ornstein-Uhlenbeck, so this will tell you that d lambda I will be almost the same, 1 over square root 2 over n dBi plus minus lambda I over 2 plus summation 1 over n lambda j, let me see, lambda j minus lambda I minus lambda j. dt. Okay. So, so this is the, you add this term. The only difference is you add this term. Now, for stochastic process, so define the L. This is the generator to the SDE. So this L becomes 2 over n d square d lambda I square plus, and this term becomes minus lambda I over 2 plus 1 over n summation over j and the d lambda I. Okay, so this is the generator of the dynamics, and the meaning of the generator is that if you start from a process f of 0, lambda 1 to lambda n of oh, sorry, I should add one more thing. So this L is a symmetric operator with respect to e to the minus n times h, well, times summation. So let me write this more precisely. This is e to the minus n of Hamiltonian of lambda. And then this Hamiltonian of lambda is a summation of lambda j over square over, I think it's over 4 over 2. Okay, I can't remember as well. And plus, just a second, minus or plus. Let me find it. I forgot the sign. Yeah, here, okay. So minus 1 over n. Summation log lambda j minus lambda I. And summation of j bigger than I. Okay. Okay. So when I say L is symmetric with respect to this means this co-measure d mu, and this means L acting on F and G d mu is equal to LG F d mu. Okay. And so then the standard notation, then you call it F, LF. This is called the Dirichlet form, and this one is okay. So 1 over n. This actually in our case is equal to 1 over n. It's 1 over 2n times integration of d I f square summation over I d mu. So I don't know if this makes you feel better, but this is actually equal to, if gradient f. Okay. Now, so, summation over I. Summation. Now, now from the SDE to this operator, this is a standard in probability theory. You take the coefficient of this guy square, and you change this to the derivative square, and this one just becomes this one times dd lambda I. So that's the standard stochastic calculus. It's once you get that, you can get down to here. Okay. It was, if you look at the Dyson's paper is very interesting. The Dyson, I don't understand physicists. Physicists seems to be born in a completely different way. And Dyson didn't use Ito calculus but somehow he liked to use the derivative of white noise. I don't know how to make that rigorous, but anyway, that's his calculation. And then he did the same thing. By the end, he came up with the same formula. And so, but it's much nowadays much cleaner to look at Ito's formula and get his formula. Okay, now so once you get that, and then so Dyson basically stop here. He never want to look at from this way. But if you are trained in the probability, you immediately will write in this way. And now, what's the surprise is the eigenvalues equation is autonomous. Autonomous. I don't know how to spell it. So the eigenvalue has an equation by itself. It does not involve eigenvector. In principle, the eigenvalue and eigenvector equation can couple. But here you see the eigenvalue by itself. The eigenvector completely disappear. So my advice, okay. So for those of you who do not know the stochastic calculus, my suggestion is the following. So you just forget about what the deep Brownian motion means. You just think about the metric elements go by a diffusion by a heat equation. If the metric element go by heat equation, then the eigenvalue will satisfy an equation with this generator L. And more precisely is the following. More precisely is if ft of lambda 1 to lambda n d mu lambda is the probability distribution at time t, then dt ft is equal to L ft. So the meaning is the following. So if you want to understand the eigenvalue distributions at time t, what you do is you solve this equation. You solve this equation, and then you take ft d mu. Then this will be your probability density at time t of the eigenvalue distributions. So you can completely, yes.
How do you know about that equation? Say decay or
Oh, that's a good question. This is the key. The key is to study this equation.
because from there you have a spectral gap and
Yeah, but that's not, yes. This is actually the key is to analyze this equation, and the spectral gap and so on will not be sufficient. And this is what I'm trying to say. So the question is, of course, now this is the equation, but this is this equation with n particles, and typical equation with n particles is not that easy to understand what's going on, and so Dyson just write down the equation, and he started to guess what's the behavior of this equation, and so here is Dyson's conjecture. Dyson's conjecture the following. it's very strange. Dyson says the time to local equilibrium for this dynamic star. Let's just call it dBm, is of order 1 over n. Okay, this is a very vague conjecture. He didn't make it precise what's the meaning of this, because the trouble is you don't know what's you have to first say what the local equilibrium means in order to say this statement, and so. And I think what I'm trying to tell you is this hour is I'll try to tell you the idea to prove that this is correct, and so they would. And now, so for those of you doing differential geometry, it's actually this operator it's almost like Laplace operator on the manifold. It's actually any operator of this type you can study just like Laplace operator on the manifold, except the manifold now is changing with this quadratic form. Okay. And now, so from now on, I will forget about everything about. So just forget about everything about this derivation of the Ito's formula and so on. You just think about you want to study this PDE. It's a linear. This is a linear PDE. Okay. All right. So so let me define what's the entropy. So the entropy of a two-probability measure is defined to be a log of times okay. So this is how I define the entropy. And then if you write the mu, if you write the okay, so sorry, nu respect to mu. Okay, so this is slightly better. So if you write the nu equal to f times mu, and s of f mu with respect to mu is integration f log f d mu. Okay, so this is standard definition of entropy, and entropy is always positive. So this is an exercise. And now the reason then there's a log solver inequality. So log solver inequality tell you that the following. So log solver inequality. The log solver inequality. Oh, let me state a theorem. This theorem is due to Becquerel and Emery. So if you measure mu, it's e to the minus h. Okay. Then the s of f is less than 2 over k d of square root of f if the hashing of h is bigger than k. So this is the Becquerel-Emery theorem. And furthermore, so if you solve equation dtf equal to L f t, then this will imply that the s of ft is less than exponential minus 2t times k of s f of 0. And the Dirichlet form of square root f of t is less than 2 over t e to the minus tk of s of f of 0. I think this one is. So in other words, so this implies the entropy is exponentially decay with rate, with time to equilibrium one over k. So that's the idea. Now, this Becquerel-Emery theorem says this is actually it's equivalent to the geometry theorem. If you study the differential geometry, differential geometry, you will say the Ricci curvature is positive, then you have a spectral gap, and you have a heat kernel estimate. And here says you have a log-Sauber inequality if your Hamiltonian H is strictly convex. And this strictly convexity give you the inverse to the time to the equilibrium. So, and if you look at the proof, this, both proof, actually the proof and this Peter Lee and Yau's proof of heat kernel estimate has some similarities, but it's not exactly the same, but because actually differential geometry is proof, the Lee and Yau proof is much more complicated because they got the pointwise estimate, and here is in terms of entropy and Dirichlet form. I think the important thing is that this gives you the time to equilibrium is 1 over k. And it's quite obvious. What they say is if you think about your a Hamiltonian like this, okay, and then the time to equilibrium, if this become bigger and bigger, then it takes longer and longer time to reach equilibrium. And if it becomes smaller and smaller, it becomes shorter and shorter. So that's why it's 1 over k. So this theorem, I have a I went through this proof about 10 times in my life already. So, but it's actually it's try to see. Try to look at this proof. It's actually it's very important argument. And I learned this. I remember I learned this from Varda, and he told me that this theorem is correct, and then he started to differentiate. So let me give you the hint at the time he gave me, and then you should try to finish the rest. So if you differentiate the entropy, then you will find this is exactly the Dirichlet form up to a constant. Okay? It's all this idea. And the idea is then you take a derivative of entropy. So then the idea is you don't put this minus negative something depending on the entropy again. And then there's some number here. I think it's k or 1 over k, I forgot. Maybe it's k here. Okay. So you combine these two inequalities, then you can prove this and this. And then you integrate this one, you will get this Becquerel-Emery inequality. So the whole proof is dynamic. You see, this theorem as it is, this inequality here, there's no time at all. But the way to prove such an inequality with no time is to go through an argument depending on time. And the hint is these two inequalities. So you can try to finish it. It took me a day or two to complete the argument. It's at a time. So details it's in the page 74 of my. Sorry, I can't hear you.
From the,
2 over t?
yeah.
Well, I forgot exactly how do we get it, but anyway, don't worry about it. You should check. I forgot exactly where it's come from, but because the interest is for large t. For large t, anyway, this is the main term. So, okay. So now we want to apply this Becquerel-Emery argument to. And so now, what is our Hamiltonian? Our Hamiltonian is actually what we have is e to the n to the n h, and we have this here, and h is this. So if you compute the Hessian of h, it computes a quadratic form. So this quadratic form, because this term, lambda j squared over 4, so quadratic form is summation over vj squared over 4. Plus, now here, this log lambda j minus lambda I, so if you compute Hessian here, you differentiate I and differentiate j, and then you times the vi vj. So at the end, this will become lambda I minus lambda j squared times vi minus vj squared. Okay, so this is the quadratic form. So let me check. Just want to make sure it's correct. I think it's correct. So. Well, where it goes. Well, okay. Anyway, I think it's correct. Anyway, you can just compare. I mean, I may make some error of. Oh, I see. There's 1 over n. Sorry. Yes, there's 1 over n. I forgot. Okay, so you get that. But don't forget there's another n here. There's another n here. Okay. So, all right. So this tells you that this tells you this tells that you get this log solver inequality, and yes. So this, in particular, this is bigger than constant. This is bigger than 1/4. I forgot 1/4, 1/2. That's all. Well, okay. So let me Hessian is 1/2. So this is bigger than 1/2. V squared. This is L2 norm squared. Okay. So, just a second. Yes, and then so what is our dynamics? How is our Dirichlet form? So now let me put back all the n. Our Dirichlet form is 1 over n summation I gradient f if squared d mu. Okay. So there's a slightly change. There's a small difference here. I divide by 1 over n, and this mu is e to the minus nh. And here I state a general theorem. This Becquerel-Emery, I state a general theorem. There's no n here. There's no n here, and there's no the Dirichlet form. Oh, sorry, the Dirichlet form again. Here the Dirichlet form of a function g is integration gradient g squared d mu. So there's no factor n here in the Becquerel-Emery theorem. So the Becquerel-Emery theorem is a general theorem, has no specific reference to the number of particles. But here in our definition, I put an n here and divide by, and I also divide by n here. But this n and this n will cancel each other. So from here, so from this bakery memory, this implies that the entropy of F is less than constant times the Ricci form of square root F. And this implies the time to equilibrium is order 1. Okay. Now, so time to equilibrium is order 1. Oh. But the Dyson's conjecture is time to local equilibrium is order 1 over n. Okay, so there's a gap. So so the question is, time to equilibrium is order 1, and to local equilibrium is 1 over n. And so why? How do you answer this question? Now, if you work on fluid mechanics, you know that in fluid mechanics, there are always, you know, there's some wave, and you also do the frequency decomposition. There are also some fast oscillations, right? So typically, the fast oscillation will relax much faster than the big wave. So this means the local fluctuation will go to equilibrium much faster than the global equilibrium. So log-Solver inequality tell you the approach to global equilibrium is order 1, but this is not enough, and so you want to see that how do you answer the question that time to local equilibrium is order 1 over n, and this is a key question. Is how do you answer this question? Okay, so let me state the main result here. It's the theorem 12.4. Maybe I stay here. Or any question here? Yes? There's an order. That's right. It does not cross. It will not cross if beta is bigger than or equal to 1. They will not cross because actually beta equal to 1 is equivalent to two-dimensional Brownian motion. Beta equal to 1 is the dynamics beta equal to 1. If you look at the gap, the distance of the gap, and you forget about every other particle, then the gap satisfies the radial process of two-dimensional Brownian motion. So the probability you will hit this point is 0. The two-dimensional Brownian motion will hit the origin is probably 0, so you will not cross. And this can be proved. And so everything we are talking about, actually this is also a fine detail, is this Bakhry-Emery theorem. Actually, in principle, everything has to be smooth. And so we are applying the theorem to the simplex, because you have a lambda 1, let's say equal to lambda 2, let's say. So you apply the theorem to the simplex, and it's actually they are very, they are serious technical questions because you have to worry about the derivative at the point lambda 1 equal to lambda 2, and whether you can do integration by parts in the right way. And so there are quite a lot of details, but anyway, it works at the end. So, but it's actually important that you will not cross. If you cross, then well, of course. So here's the main idea. So this is so-called the local. I'll try to state this. What's the name? I don't know how do I call this name. I changed the name several times, so now I forget about the name. A local relaxation measure. This is it's somehow a little bit crazy idea. So you define a measure mu tilde is equal to I call it omega. Okay, I call it omega. Omega. It's equal to omega x dx, and omega x is equal to e to the minus n h tilde divided by z tilde, and h tilde is equal to original h plus w, and the w is equal to 1 over 2 tau xj minus gamma j squared. Okay? So gamma j is the classical location. Remember, the gamma j is defined by this formula. This is j over n, and this is gamma j. Okay. And then, so the idea, so this xj is lambda j. So xj. So you change your measure. So in the beginning, our equilibrium measure, invariant measure, is d mu is e to the. This is d mu. Well, so now I take a measure which is different from the invariant measure. I change this one by add a new potential which is convex, and tau will be small. So why do I do that? Because the Hessian of h tilde will be bigger than 1 over tau. And now because tau is much smaller than 1, so this is much bigger than 1. At the end, our goal is to choose tau. It's almost n to the minus 1 plus epsilon. So this is the goal. Okay, so I choose a measure which I completely change the invariant measure to a new one. And this new one has a beta convexity by adding this term. And now, so the theorem says the following theorem. It says for any t bigger than tau times n to the epsilon, the entropy of GT of Ft of mu with respect to omega is less than constant m squared times q times tau inverse, and q is equal to where is the q? Yeah, q is equal to summation so I go back to lambda j. I don't want, maybe it's a better idea to use gamma j, lambda xj. Okay, and 1 over n. Now, so the theorem says, suppose your equation like this. Then and q equal to that. And furthermore, if I define, I will explain what's the meaning of this. If I define the, if I let ft of the ft of mu plus the gt of omega, then the Ricci form square gt respect to omega is less than constant as n squared q tau minus 2. So this is the key estimate. So let me try to explain this. So usually you always control the entropy with respect to equilibrium measure. You also compute the Ricci form with respect to equilibrium measure. Now, but then the equilibrium measures, if you look at this, the equilibrium measure has time to equilibrium order 1, which I just, it's order 1. So now, so then this means we cannot use this Becquerel-Emery's argument. So the idea was, now if I change the measure to a different one, this one is much more convex, because I add this term to make it artificially convex. But on the other hand, because I changed the measure, so then the original estimate of Becquerel-Emery is incorrect. But on the other hand, I still know that the entropy at time t, as long as t is bigger than tau times n to the epsilon, is controlled by n squared times q times tau inverse. And what is the q? Q is the distance between lambda j and the gamma j. Taking the expectation with respect to the ft of lambda mu d lambda. And then you also get the estimate of the Ricci form. But anyway, this one is, well, this is a secondary, but this one will be the important one. So, so what it means is that if you know the lambda j is close to gamma j, then you will know that the entropy of your ft of mu and the omega are very close. So, so this is something. This is some unusual step because instead of compare thing with equilibrium, this is equilibrium measure. So you don't compare things with equilibrium. You compare things with something which is non-equilibrium, which is actually a wrong object. You compare your you look at the entropy between your measure and the probability measure, which is wrong. But on the other hand, you can control this as long as you know the q, you know the distance of lambda eigenvalue lambda j and classical location is not far from each other. Then you can really control this one. And what's the point of this? Because why do you want to estimate this guy? It's because this omega has good convexity. This omega has good convexity is because you get this one. You can get from here. Probably you may want to look at this for a few minutes. This is actually quite strange that you are trying to do this. And then, so I will explain that this one and why the next with this one and why you can conclude the Dyson's conjecture. So I will state, in making the following statement. So, yes. Z tilde is normalization constant. So anytime I write something like that, because this is probability, I want this to be probability measure. So I need to divide it by a constant to make it probability measures. Okay. So, by the way, this idea has never appeared anywhere to study a problem by convergence to equilibrium by using by using a probability measure, which is not in the equilibrium. And so there's the reason there's the following theorem says if you have a density q d omega equal to 1, and then if you compare the q d omega minus d omega over test functions, or g, I call it g, or g of n of lambda I minus lambda I plus 1, and so then the summation over I belong to a set J and 1 over the size J, then this is less than the T times the Ricci form omega of Q divided by J square root of T is inside. So roughly speaking, it's it says if you Q of T, so it's T Q well, plus square root entropy of Q e to the minus CT. Maybe I think it is slightly more complex. So let me just drop it. We just put this top. It's just tau. Okay. All right. So it is tau. Tau is defined. It's here. Tau is defined. Okay. So this is the following. So suppose you want to look at the gap distribution of eigenvalues, summation over I between in the J, and J is a subset. J is, for example, J is a subset so you take a subset of these. So say, for example, roughly speaking, if you take energy E, and then you can look at all these indices called J. Okay. So you take the gap of eigenvalues, and then you take average over this gap. You compare the expectation of Q omega and the other one is just omega. The difference between Q omega and omega. The difference is controlled by the Ricci form of this Q with respect to this square root Q of the Q with respect to omega, and times tau divided by J. So in other words, if the Ricci form of square Q omega is small, then this implies the gap distribution of omega, Q omega and omega are the same. So that's the idea. So roughly speaking, we tried our dynamics as invariant measure of mu. We construct a measure which is completely wrong, but it has increased the convexity. Now from here, you can control the entropy and the Ricci form. And now once you have a good control of the Ricci form, and this lemma tell you that if you have two measures, and if their density has small Ricci form, then they have the same gap distribution. So this means this gap distribution. So the theorem says, so this will imply that this GT omega and the omega has the same gap distribution. So this is the logic. And then you combine these two theorems together, you prove this Dyson's conjecture about the time to equilibrium. But our original theorem is to prove this Wegener theorem. Wegener theorem has no Brownian motion at all. So there's still one more thing I should say, but I know the time is up, so I just take 2 minutes. So in the beginning, we have a regular matrix H. And then here has a Gaussian. And you want to say the eigenvalue of this one and this one are close to each other. So what we prove now is if I take a H and I add the A, and this is Gaussian. And then I know that after I make some small perturbation, then the eigenvalue of this one and this one are close to each other. They are close to each other. But our original problem is this and this are close to each other. So there's still something missing, because when I run by Dyson-Brownian motion, I forgot to say, when you run by Dyson-Brownian motion, it's the same as you take original matrix but add a Gaussian piece. So you add a Gaussian piece, and then you said you add this and this is the same eigenvalue distribution, but this does not mean the original H has the same eigenvalue distribution as this guy. So this is a bit like you're using a flow argument, and your flow argument at time t will close to your solution, and this is what you want. But you're interested in your time equals 0, that it has to give the same eigenvalue distribution as the Gaussian case. See, whenever you run in differential geometry, you run the flow argument, you want to say the time goes to infinity, you flow to something you try to prove. But now the time at infinity in this problem is a Gaussian, is completely trivial. But so now what you know is if you run the dynamic for some small time, for some short time, you will go to, it's already reached the equilibrium at infinity. But your question is, the question you want to study is at time t equals 0, your initial data. So how can you study the initial data by running the dynamics? This is the opposite of what you thought about the flow argument. And so next time I will explain the idea. Of course, I will go through a little bit some of this detail, and also explain the idea why you can study the flow, why you can use a flow argument to get the initial data is correct. Because it sounds contradictory. I mean, I don't know if you catch the logic problem. Because, you see, okay, so you want to say that H0, this is initial data. The eigenvalue distribution of this one and the H infinity, this is Gaussian. You want to say the eigenvalue of this one and this one are the same. Okay? So what you do is go to time ht. Okay? Then you prove that at the time ht, then they are the same. So this is this Dyson-Brownian motion argument by running the flow. So this and this are the same, but then you want to say that this one and this one are the same. But then this sounds very strange, because if I can prove this one and this one the same, but then why not I just directly prove this and this is the same? What's the difference? And also there's a logic question of, in all this argument based on this Becquerel-Emery argument, actually the initial data does not really matter. Because when you show that it converges to equilibrium in a very strong sense, the initial data, it doesn't really matter. The dynamics will force you to equilibrium. So this means that you use almost not very much information of this guy. So logically, there's a problem of how do you answer this initial layer question problem. But then we will explain that actually you can do something to say that actually initial layer, there are some way to almost go backward in time, say this and this guy are the same. And then this will finish the proof from here and here are the same. So this is, I will do this next time if you're still patient to follow. Okay, all right, I'll stop here.